Sub-Project 1, the Coal Slurry and Trained Bed Gasifier High-Performance Swirled Burner. We described the development of a laboratory-scale coal, water slurry and trained bed gasifier. A coal, water slurry atomization burner with a flow rate of between 10 kg per hour to 20 kg per hour is developed. We explore the characteristics of the flow field for the coal, water slurry atomization burner and gasifier using experimental measurements and numerical simulation methods, and then build a laboratory-scale gasifier based on the simulation results. One type of slurry liquid was tested in the study. Sub-Project 2, Medium to High Temperature Dust Removal System. Granular bed filters are separators that utilize solids such as quartz, sand, gravel, or limestone as a filter medium. In this study, moving granular bed filters (MGBFs) have been employed to remove dust from mid-high temperature gases and have several advantages, such as the ability to operate in high-temperature gases, a high collection efficiency for fine particles, low operational cost, and a long operating lifetime. The bed medium captures solid particles from the gas stream via the mechanisms of inertial impact, diffusion, and gravity. The moving granular bed filter device consists of a filter bed system, an air fan, a screw feeder, a pitot tube, a sampling probe, a filter granule supply device, a rotary valve and a trommel screen system. Sub-Project 3, Removing Toxic Materials including mercury and arsenic. In this study, a test rig for removing the toxic elements of mercury and arsenic has been established as illustrated in high-temperature mercury removal system. This system includes a mercury vapor generator, adsorbent loading part in the furnace, temperature controller and mercury monitoring unit. First, the ppm to ppt level of these key elements can be accurately determined using the atomic absorption analysis technique. A series of screening tests were conducted using potential materials for the removal of mercury and, as under hydrothermal conditions, knowledge of the experimental parameters such as physical and chemical characteristics, including surface area, removal efficiency and reaction temperature is beneficial to explore the scrubbing system for these elements. Sub-Project 4, CO2 capture by pressure swing adsorption. 2 PSA processes, a 2-bed 6-step process and a 2-bed 8-step process, are studied to separate CO2 from the effluent stream in the water-gas shift reactor. The effluent stream, as cited in the final IGCC report of the DOE, has a composition of 28% CO2, 40% H2, 5% CO and 27% H2O. We assume that water is removed before entering the PSA. Therefore, the inlet composition is 38.36% CO2, 6.85% CO, and 54.79% H2. Sub-Project 5, Syngas combustion. The recently built double-chamber high-pressure pre-mixed turbulent combustion facility is shown in photos. There are 4 pairs of large quartz windows installed at the front and back as well as on the top and bottom of the high-pressure pre-mixed combustion facility, including both inner and outer chambers, allowing flexible optical access for direct visualization and PIV measurement of the reacting flows. The Syngas air premixtures have a composition of 65% CO, 35% H2 and are used at 2 different equivalence ratios equals 0.5 and 0.7. The steps for realization of the high-pressure explosion experiment are detailed below. To begin with, both the inner burner and the outer chamber are purged by dry clean air, after which the inner burner is deeply evacuated, during the process of gradually filling the combustible gas mixture into the inner burner to the wanted pressure condition. The outer chamber is simultaneously pressurized using air controlled with a pressure value to at least equivalent to or slightly greater than the pressure inside the inner burner. Sub-Project 6, IVIED platform for plant simulation. In this section, we describe the building of an integrated platform capable of adopting various simulators to evaluate the system performance of the chemical or power plant. The Commercial Chemical Process Simulator, PRO2, is adopted in the present work to analyze the system performance of the integrated gasification combined cycle method with CO2 capture. There are 4 major blocks in the reference IGCC plant: air separation unit, gasification island, gas cleanup unit, and combined cycle power block. Additional water-gas shift reactions and CO2 absorption processes are integrated into the gas cleanup system for CO2 capture. Cryogenic air separation is employed in the ASU. This is the most common technology for efficiently and cost-effectively producing large quantities of oxygen and nitrogen. The slurry-fed and trained bed gasification technology is used in the gasification island to convert solid fuel to synthesis gas. A Selexol-based absorption process is adopted to remove sulfur compounds and CO2 in the gas cleanup unit. A combined cycle, which consists of a gas turbine, heat recovery steam generator and steam turbine, is employed in the power block to generate electricity.